Climate protection is quite profitable, even if you don't think it's necessary, because saving energy is cheaper than buying energy. So two of our biggest chip-making firms have been routinely cutting their carbon emissions 6% a year with 2 or 3 year paybacks by fixing their existing plants. DuPont set a goal that by 2010, with 6% gains in annual energy productivity and some shift to renewables, they would cut greenhouse gas emissions to 65% below the 1990 level. Actually, by 2006, they were 80% below the 1990 level, and they'd made $3 billion U.S. profit by substituting efficiency for fuel. Dow Chemical did even better than that. BP met its operational carbon reduction goals 8 years early. Yet they bashfully said no net cost, so I inquired, and they bashfully admitted that they had actually made $1.6 billion U.S. profit on that deal. General Electric is in the process of raising its energy productivity 30% to build shareholder value. Interface built the most oil-resistant cost structure in the carpet industry, cutting its total greenhouse gas emissions by 5/8. In fact, in the carpet business alone, by 4/5, while growing the business very profitably. Texas Instruments recently commissioned a new chip fab building in Texas using a fifth less energy than their previous design without using the two biggest energy saving recommendations, which would have taken that around 50%. Those were still being tested at the time. And they also saved a third of the water and 30% of the capex. And it's because it was $230 million U.S. cheaper than expected to build that they were able to build it in Texas, not China. So the politicians keep debating the theoretical costs of climate protection, but smart companies are racing to pocket the profits before their competitors do. We've now demonstrated this in over $30 billion U.S. worth of facilities, starting with retrofit designs for 8 chip fabs, saving often upwards of half the energy used to make chilled water and clean air, paybacks averaging about 2 years. We took the most efficient oil refinery in Europe and were able to find 42% savings with a 3-year average payback, 50% savings in getting the rest from things they're throwing away at a North Sea oil platform, over 40% savings with few-year paybacks at the world's second biggest LNG plant, even bigger savings with new trains, big savings at a big platinum mine, world's biggest, or $1 billion capex saving and 62% energy savings at a Fischer-Tropsch GTL plant. Now, our next new chip fab design after the Texas Instruments one I mentioned eliminated all 22,000 tons of chillers and should save about 2/3 of the electricity and half the capex. Our original data center designs were saving about 89% of the energy with somewhat lower capex and better uptime. The latest one we've done is 80% savings before the software improvements, which will be a lot more, and saving about half the capex if they have the guts not to build the chillers they won't need, which is all of them. Otherwise, it only saves 20% of the capex, and the uptime should be better by an order of magnitude. We recently designed a mine for an equatorial country that is powered by gravity, no fossil fuel. Supermarkets, huge savings. Chemical plant, another kind of chemical plant. Altogether, on retrofits, we normally save about 30 to 60% of the energy with 2 or 3 year paybacks. If it's a new facility, savings are more like 40 to 90%, but capex in almost every case goes down. So we've now tunneled through the cost barrier in altogether 29 sectors. Of course, if the plants had been properly designed in the first instance, we couldn't have done any of this. So we're hatching a plot for the nonviolent overthrow of bad engineering involving a casebook of very high brain velcro examples set in facing columns with the normal way to do it, and reinforced by demand pull, in which the heads of large firms that buy a lot of engineering services will ring up their favorite deans of engineering and say, we've just tested this new casebook in our practice, and we can't hire your graduates unless you teach them this way, because they won't be able to produce the breakthrough results that our competitive success requires. That will tend to change the pedagogy faster than waiting for the old profs to die or retire, which is the normal time constant. Now, each company has its own piece of that opportunity. Mr. Liang Lok, sitting here, and his team have told me of some interesting cases they've worked on. One was a back-end fab in the region in '97, mainly by fixing the mechanicals. They were able to cut the energy used per chip by 69% in 11 months with a 14-month payback, and then went on from there. The excellent efficiency of the Ang Mo Kio fab in Singapore, the front end from ST Micro, started off with under a year payback with a few years effort, and then altogether, if you count 91 through 97, they saved $30 million, and the energy intensity per standard wafer went down 60%, which provided 80% of the energy capacity for a 3.5-fold increase in output, and 80% of the measures paid back within a year and a half. What most impressed me is that those retrofits were done during continuous operation, with over 20 each of cryogenic freeze plugs and hot taps. Most impressive. Now, what this was doing, nonetheless, despite the size of the numbers, is just harvesting low-hanging fruit that's fallen down and is mushing up around the ankles and spilling in over the tops of our boots. Meanwhile, the innovation tree keeps dropping more fruit on our head. Of course, none of this would have been possible if the fabs had been optimally designed in the first place. But like most factories, they were designed with infectious repetitis. That is, we copy the previous set of drawings because we know it worked. And the copy exactly mentality of, say, Intel is understandable in the manufacturing process, which is so delicate, and there's so much that can go wrong, and one must always verify the witchcraft that makes it work. But it really doesn't make sense in the utility side, where you're just producing something like chilled water or clean air, and where we want continuous improvement, the very opposite of copy exactly. I actually was once in a fab where a certain pipe overhead made a right-angle bend round an invisible obstacle. I asked what that was about, and they said they'd been told to copy exactly the piping diagram from the previous plant where there was a structural pillar in that location. I never found out what happened to the pillar. Or here's a very simple example of retrofitting a large petrochemical complex. They were making, forgive the barbaric units, 1,300 psi steam, but not cogenerating with it. Well, either they should cogenerate it with it or they shouldn't make it, because what they were doing with it was just throttling it back. And also there were pressure letdowns elsewhere in the system that could cogenerate over 10 megawatts with a present value of $45 million. A boiler could be replaced with another carbon monoxide burner. General Motors had offered to give a free high-temperature fuel cell for testing, and this would burn all the hydrocarbons very nicely. They vented a lot of steam, but of course even the 50-pound steam was good for absorption chilling, which would save condensate, and it would save a 3-to-1 ratio of 130-pound steam. There was a strong opportunity for innovation and optimization and control in the furnaces. The high-temperature heat that they were throwing away, paying to throw away, could be used to distill water for better water chemistry in the boilers and for the cooling towers and fin fans. They could distribute and optimize their distillation, integrate with some nearby facilities they owned or owned by others. They could compress air only to the pressures actually required without letting it down, and they had a good shot at actually eliminating compressed air, which is generally a good way to start. They could much improve their sensors and the graphical presentation of their data so the operators would be able to work better. And they could use high-efficiency cooling towers, do some overcooling, maybe summer sink with well water. And This may sound terribly conventional, but it added up to extremely large and profitable saving opportunities. Now, ST set some interesting goals for CO2. When we showed them in 99 how to cut CO2 per chip by 92% profitably then and 98% profitably in a few years, they adopted a 90% cut goal for 2000 and zero CO2 by 2010, even though in 2010 they expected to make 40 times the chips they'd make in 1990. And they would achieve this by doing a lot of their supply from fuel cells and combined heat and power, a little from renewables, and their carbon per dollar value added would be less than a fifth what it was in 1990. So they were projecting that by 2010, their carbon reduction would be over 10 megatons and worth, at the old energy prices, nearly $1 billion, along with perfluorocarbon reductions, at least tenfold, which was another over 10 megatons equivalent. How do you do these big cuts? Well, think about it in steps, like links in a chain. Just the 300 millimeter shift for the same yield multiplies your CO2 by 0.44 per chip output. State-of-the-art fab efficiency saves another 70%. On-site trigen net of reformer loss another 60%. Eliminating the UPS losses another 6%. Fueling with gas, not coal, because it's less carbon intensive, another 50%. Switching to half renewables, another 50%. Multiply it out, those 6 steps cut your CO2 per chip by 99%. So if you produce 30 times more chips, like 18% a year growth for 20 years, and you fueled your growth in this way, your total CO2 would go down nearly threefold, so you could sell carbon permits to your competitors. Almost all these steps are profitable now, the rest soon, and all of them can bring big operational benefits. And I'm not counting stuff further upstream like the 4 or 5-fold savings we can now do on the energy used to make Czochralski silicon. If you look across the entire range of industry, I don't think there's any limit in sight for a very long time to how efficient we can get. Industry is a materials processing activity. I mentioned that 99.98% of our materials are wasted. Either they never get into durable products, or after they do, they don't recreate value, they're just thrown away. And as we dematerialize, that is, we make more artifacts with less stuff and better design, and we virtualize, and we make things last longer and close the materials loops and do integration between plants that can use each other's waste to create value, and then ultimately we'll get to desktop manufacturing, most of that waste is going away. There is, of course, a lot of conventional innovation continuing with better technologies. There are important new kinds of processes like microfluidics. You know, in a typical chemical works, most of your effort is not to do the basic reaction, but to separate the product you want from all the unwanted side products that came from side reactions occurring when the conditions of the reaction were not perfectly controlled. So in microfluidics, you have a stack of a bunch of typically silicon wafers with millimeter scale channels etched into them and little reaction chambers where you can very precisely control the mixing temperature, pressure, and time catalysis so you get only the reaction you want. The side products aren't made in the first place, so you don't need to separate them. And you can often reduce the size and cost of that plant by orders of magnitude along with its energy use. Efficiency, of course, keeps getting bigger and cheaper through better technology, but the tunneling through the cost barrier through integrative design is the really big key we've got now. But next coming at us are 2 further design revolutions. One is innovation inspired by nature. Please read Janine Benyus's book, Biomimicry. It will just blow your minds about how nature has already solved your design problem. You just need to know which organisms to ask how they did it. And maybe nanotechnology in Eric Drexler's sense of self-assembling molecules at a molecular scale. Although I would add a word of caution about both of these. Nanomaterials are turning out as expected to be rather biologically risky, And biomimicry is not the same as biotechnology. It's really the opposite. Biotechnology will take a spider gene and put it into a goat where it doesn't belong, so that the goat's milk will contain spider silk that you can then extract and make into things. Biomimicry will figure out how the spider makes the silk, the stuff that's tougher than Kevlar, stronger than steel, and it's made in ambient temperature and pressure under life-friendly conditions in the spider's belly out of digested crickets and flies, and then will imitate how the spider does that. That's biomimicry. Very different. And over time, I think you'll find Darwin always beats Descartes. And then there are the options we haven't thought of yet. So if we get good at responsibly combining a large forebrain with opposable thumbs, this zany evolutionary experiment we're engaged in, maybe we'll be around long enough to think of still more good ideas, but we certainly have plenty for now to be getting on with.